Alright, so in this video I'm gonna be explaining another article about domain adaptation, and here this article, Hardness-guided domain adaptation, and we are using it for the task of biomedical named entities because it's very expensive to create all labels. So labeling is expensive, so we have low resource. Sometimes we have low resource and we have data scarcity. So this paper from Monash University in 2022. Domain adaptation is an effective solution to data scarcity in low resource scenarios. Because, for example, you have a very rich data set, we call it source domain, but you also have a very small data set that it is not as rich as the source, so we call it target domain. We want to reduce this domain shift, and we have 3 different domain shifts: covariate shift, and this is the simpler things, label shift, and also concept shift, which is very difficult, concept shift. So when applied to token level tasks such as BioNER, which is a good data set for name entity recognition in biomedical text, domain adaptation methods often suffer from challenging linguistic characteristics that clinical narratives possesses, which leads to unsatisfactory performance. So we present a simple yet effective hardness-guided domain adaptation framework for BioNER tasks that can effectively leverage domain hardness information to improve the adaptability of the learned model in the low-resource scenarios. Experimental results on biomedical datasets show that our model can achieve significant performance improvement over recently published state-of-the-art meta-NER. So you see the score of each of these examples. These are examples of domain hardness scores for tasks generated from 3 domains. For example, domain of gene, domain of drug, domain of species during a training procedure. The score is based on a scale from 0 to 1. The higher the score, the more challenging the domain is. So given a set of biomedical corpora from multiple source domains, we aim to learn a sequence labeling function from a set of tasks sampled from these subsource so that each can be adapted to a new task sampled from target domain. And this function should contain a sentence encoder parameterized with theta that captures the contextual information, a tag decoder parameterized with phi that assign the entity tags to these words. Thus, the learning objective is to search the optimum. So theta is for your sentences, and phi is for your parameters for your tags. And of course, we assume that there is no intersection between your support and query, because in this paper they define the support and query set. We further restrict both T-source and T-supports and T-query to contain only K sentences respectively, sampled from a domain source. This value of K is dependent on the amount of data we have during adaptation phase. And this is to mimic the same few-shot setting, because in few-shot setting we are talking about query and then support. And to regularize theta, It includes, the model includes a domain classifier as a separate head on top of the sentence encoder. So lambda controls the trade-off between your labeling loss and the classification loss. And you see, you update the gradients, the parameters using this gradient, and you have this by level optimization here, because you have two losses, label and classifier. But here we are getting from source domain. Here require your support and target, and query. So the corpora is, for example, you have different data sets for different entity types. For example, if you use NCBI, most of this is entity type, that's disease entity. But if you use this JNLPBA, this is for genes, mostly about genes, about 25,000 unique tokens, and 81% of sentences have name entities. So you can go from this source to this target if you have rare data. For example, here we have 12,000 tokens, but here only have 205, or so you can go from different source to different target domains. But what about task hardness? Although picking the case sentences with name entities is shown to improve the domain adaptation performance, it is not realistic in practice to have only sentences with name entities and wasteful not using the sentences without name entities. So the defined task difficulty. So this is the task difficulty for classification, labeling, and loss. And you get for different, for example, for disease data set, the disease entity, you have two different data sets and you can see for different models, you see if you use BioBird, then their font performance of NCBI is just 30%. And you can increase the size as well. And this is the precision. Previous one was font score. Here is precision. And here is recall. So we have proposed simple yet effective methods that effectively leverage the domain hardness information to improve the effectiveness of learned model under the low resource NER setting. Experiments on biomedical corpora have shown that the sequence labeling function derived from our HGDAs have achieved substantial performance improvements compared to current state-of-the-art baselines.